Hi and welcome to class 8 of modeling and texturing photoreal environments. In this class, we are going to be looking at creating ground surfaces and ground structures using Agisoft Photoscan and ZBrush. As you can see in this sample scene we've got here, Agisoft Photoscan is amazingly good at recreating ground surfaces and ground details in both geometry and texture. Not only is it extremely accurate at creating ground surfaces, it's extremely fast to process compared to objects like trees, vehicles, and even people. It's so efficient and so quick to accurately create ground surfaces. I dare say it's even designed specifically to work best creating ground surfaces. So the scene we're actually going to be working with is this scene here, which is quite a large data set which has all the texture and geometry detail in it for about a 70 meter by 10 meter wide rock ground surface in a rainforest. And this gap here is where I've rotoed out the water, which is a waterfall that flows down the middle of it, which you can put in Unreal Engine or in RenderMan. The scene I've used in the Brother lighting course for this course uses a RenderMan river down the middle here, and once it refracts all these rocks and surfaces in here, it looks really great when it reflects all these surfaces with a displacement map on it. So that's the scene we're going to be working with to look at how we create ground surfaces. Now, ground surfaces, if we have a look at the dense point cloud, there's a few things you have to keep in mind and plan out when you're creating ground surfaces for VFX scenes. And one of those things is that a flat ground surface often has a few tricky elements about it that make planning important. The first is the differences in elevation. For starters, most flat ground surfaces in real life aren't actually flat, and you'll find that out pretty quickly after you bring them into a 3D modeling package. If we rotate this to see that the tree trunks are now vertical, we can see here that this flat ground surface is higher on the left side and goes downhill on the right side. And if you had a topographical map of this area, you would see that that's the way the rock goes down this hillside, is that it's got a change in elevation. The other thing that you can see is that it's very uneven. It's not consistently flat like a texture across the surface. It actually changes in angle and changes in pitch as it goes along. The other thing is some of the rock is very flat and other parts of it come up as in on the edges of this riverbed, and that's probably where the water has flowed over this flatter section of rock over time, whereas this section of rock here has had the water flow in front of it. So instead of being flattened out by the particles of sand and grit and things that are in the water over all those hundreds of years of erosion, or thousands of years of erosion, this rock here has stayed intact that's on the riverbed, whereas the rock where the water flows from all the runoff, it's actually quite flat and worn down. Another thing to keep in mind when you're making ground surfaces is how they interface with the surrounding vegetation and rocks. You can see here we have a very complex interrelationship between where the rocks and water is and where the plants are and where these rocks are and where these trees are. And then this big hero rock here that joins into that environment, which has its own plant life and different ferns and lichens and mosses that are growing off it. So the ground is a complex thing, and you really need to plan it and design it and figure out what parts of the scene do actually make up the ground and how you're going to cut it up and modify it to work. So for this part of the scene, for example, you've got to figure out, do I include these roots in the ground scan, or do I exclude them and save them as a separate asset, especially seeming as they join into this tree up here and they're actually part of that tree's trunk. The other thing is, do you save the base of these trees and where all their leaves are as the ground, or do you cut them off and then they're a separate asset? All of that you need to plan out in advance when you're building the scene. So the way I organized this scene, so that I was able to keep the complex interrelationship between these different surfaces and objects, is I excluded as much as I could all the foliage from the scene, which ended up being noisy scan data that wasn't really useful. And I also excluded the water from the scene, and I split it up, but I kept in the tree trunks, the base of the tree trunks, and all these rocks that connect straight into the water. So they're all included in one scene. And the way I broke it up was I sliced up each section of this rocky ground surface into 5 meter wide, 5 meter long, 10 meter wide sections. So each section is trying to get as much of the scan data and texture data as possible, because of course you can put speed tree and or grow effects, plants and shrubs and trees over all of this edge part of the texture and geometry, which is what's there in real life anyway. They've just been rotoscoped out of this scene. The other thing that you need to put in is a base geometry layer that's got manual texture maps and painting in Photoshop, so that you've got these holes filled in, so that when the water refracts through the bottom of the rock, you've got a rocky kind of generic surface under there that matches the color of the surrounding rocks, so that you're able to correctly refract the correct color when the shaders reflection and refraction works. So that's basically how it was done. So it was broken into 10 sections, which were 16K texture maps and 5 million polygon high resolution meshes. And that's the way that this was all broken up, was into slices that went all the way up to the very end of the valley. And I found that that was the most quickest and most efficient way to break up the scene, using the same dense point cloud that has the consistent interlinked whole environment. So you don't need to rotate and translate and do all these different tricky things to different sections that are completely separated from each other. Instead, all you have to do is move the bounding box along, which is here. All you have to do to create each section is literally move the bounding box from one section to the next, and that's section B, that's section C, that's section D, and that's section E. And that's the way you can easily create it. Now, you might be asking, why don't you just mesh the entire scene and put a massive texture map on it, or put hugely tiled texture maps? Well, if we pull this bounding box to cover the entire scene and make sure it envelops everything, if we go up to workflow, build mesh, and we have it on a very high setting, which is required to get the detail out of the model. If we put it to face count high, what we can see here is we're getting a 24,844,000 face mesh. Now, the problem with this could actually process quite easily and will actually give you a mesh with that much detail in it. But one of the problems with generating a mesh that is that high res is that it's going to be a single piece of continuous geometry that's going to cover a very, very large area. Now in VR or in VFX, you're going to be wanting to get a very, very high level of detail in a very small area of, say, like about this big, because that's going to be directly in front of the camera. If we have a look over at our renders from the lighting course, you can see here that even the detail of this little section, which was done with a 16K texture, it only just holds up rendered at 4K. You can see here that with depth of field on these texture maps look fairly sharp, but if you were going to move closer to these rocks, you'd be looking at higher resolution still, like 32K or 64K. And if we have a look at this this scene here, we can see that when the camera is really close to the objects in the scene, you really need a lot of resolution in the textures and a lot of resolution in the geometry. So even though 24 million polygons sounds like a lot, it's actually almost not enough for the size of the area that we're dealing with. It's much better to actually use lots and lots of sections of maybe 4 meters by 4 meters wide and then 4 meters high, and then actually jam in as much polygons and detail into the textures as you can in smaller sections, rather than just using this ridiculous huge mesh that wraps over the whole thing. The other thing is you can load little sections one at a time, and you can texture them and UV them one at a time. And this kind of level size of mesh and model would be very difficult to UV unwrap, very difficult to sculpt in ZBrush, very difficult to load and render in Maya as well. Whereas splitting it up into sections can make life a lot easier, more efficient, and not only that, it processes faster in PhotoScan. So overall, it's just a much better idea to do it in sections, so that you're able to save time with processing and also get more accessible and more manageable data that you can easily modify and use. The other thing is, before we finish with that, is with textures. So if you're going to build the texture for these models, and you're going to basically wrap the entire scene in geometry, and it's going to be 50 million polygons or something, you're going to have a difficult time. Mapping all the textures for that whole area. You'd have to use maybe like 100 or something 8K textures to be able to cover that area. And even if you did that, you'd probably be looking at some fairly low resolution texture detail using trying to texture such a large area. Much smarter to break it into sections texture-wise, so that you're able to get the maximum detail and resolution out of your textures, because in the actual scan data itself, you can see here that our sparse cloud looks very lacking of detail, and even our dense cloud seems to be like okay, but when we look at our textured model, there's just a phenomenal amount of photoreal detail in these textures, which creates a lot of variety and a very natural interrelation between water, rocks, leaves, and moss and everything. And it would be very difficult and time consuming to hand paint that in the same time that photo scanning can generate these textures and map them onto the geometry. So basically, you want to get as much texture detail as you possibly can out of the data that you've gone to the trouble of photographing. So if we have a look at some of these photos of these ground rock surfaces, you can see here that they're very close up to the rocks, and there's a lot of detail in each photo that can actually be mapped onto the rocks. So all these leaves and slime and moss and cracks and grass and things like that, that all can just get mapped onto the textures for just one small little section of these rocks. So once you're actually building the entire finished thing, you can actually extract huge amounts of texture detail out of these scans that can really pay off when you go to build these models, if you build it in cut up sections that are as small as you can manage them. So that's a little overview of setting up ground surfaces. What we might do is we'll have a look at importing this data set into a new PhotoScan scene, and we'll have a look at some of the differences. Because we've already done a root system and a tree, I'm going to mainly focus on the differences with ground surfaces as opposed to just redoing the same training and methods in the software. I'm just going to focus on different ways and tips and techniques so that you can get the best possible reconstructions and data and textures and geometry out of ground surface scans, because it's a little bit different to other objects. So let's go ahead with that, and we'll open up a new scene and bring in these photos. So the first step to building this ground surface is we're going to go in and add the photos from the data set, which is in this folder called Rock Ground A1. So this is going to have more than the photos that we need to build the scene, and it's got a variation of close-up and far-away photographs of the scene. Now, the first step when you're going to edit these photos to get the best result is you want to try and roto out the water, roto out background trees and things that you don't need, and also disable any photos that have got blurry edges on them. Now, interestingly enough, when I photographed this scene, I actually photographed down the waterfall of the rocks, but it wasn't able to resolve the 3D geometry of this part of the model. So it'll be interesting to see if you want to additionally use these photos, which is down the waterfall of the rocks, which is the front part of this rocky surface, and use them in a separate photo scan scene. You can have a look and see whether it will reconstruct the downwards vertical part of the waterfall as opposed to just the flat top part. But I thought that was interesting, that it was able to perfectly recreate the flat top part of the waterfall, but it had difficulty doing the vertical part. But anyway, you can always get over these things by using multiple scenes and breaking them up to get the results that you're after. So the first stage is you need to go through these photos and disable any camera that's got motion blur or blur in it. Now, this can be caused by depth of field, or the camera being moved when you're taking photos, or the f-stop being too high while your exposure's set too long, all kinds of things like that. So the first stage is to go through and disable the cameras that are too blurry, because they can negatively impact both your geometry reconstruction and your texture maps. So don't just disable all the photos in the whole scene. Just go through carefully and select which ones you think are not sharp enough or have too much motion blur, and just disable the cameras, and that'll help when you're constructing the scene. The second thing you can do is you can mask out the water out of the scene, and that will assist in reconstructing the ground surfaces. The other thing you can do is leave the water in, and it will attempt to reconstruct this brown surface here, but it can also cause errors in depth creation. But I've found that it's actually been successful in recreating some of the water surfaces as long as they're flat and they don't move. Like, for example, beside this rock, it was able to recreate this brown water here with the submerged palm leaves under it, which looked great once it was rendered as a texture. So it recreated all of the water in this front area except for these shiny highlights of rapids that were coming down. So that was a pretty cool feature of the software and how clever it was at reconstructing the surfaces of the water. Now, with regards to the trees, you can either roto out the trees using masks in PhotoScan before you create it, before you go to create your camera reconstruction, or you can simply delete the sparse point cloud of the trees after it's been built. However, if you roto it out first, it'll create the camera matching quicker, but it also takes a lot longer for you to manually go through the photos and mask out the trees. So just keep that in mind when you're creating these scan assets. So when you're ready to align the photos, go up to Workflow and you can select Align Photos. Now, because there's 777 cameras in this photo selection set, what we're actually going to do is we're going to set the accuracy to high, but we're also going to set the pair pre-selection to generic. Now, what pair pre-selection does is it will go through the photos at lowest or even at a lower setting than that and actually figure out which photos are adjacent to each other in the photo set. For example, these are roots. It will figure out that these two cameras are adjacent to each other, whereas these cameras here are not adjacent to each other because they're actually the other end of the rocks. So rather than looking at the points between this camera and this camera and trying to find matching parts of the image, it's not going to worry about processing that, which speeds up a lot of time because it's not looking through all 700 cameras to match points. It's only looking through the cameras that have overlapping features. So basically what it does is it goes through and does a rough pass of overlapping the cameras and figuring out their position, and then from that it actually does the final alignment at high quality. So that definitely speeds up the process when you're doing it. So let's give that a go now. So we'll go Align Photos, set that to high, pair pre-selection to generic. Now we've got key point limit set to 40,000 and the tie point limit set to 1,000. So we're going to press OK on that and let it run. And when that's finished, we should have we can evaluate whether or not the cameras are in the correct positions and see how that looks. So we've got our sparse point cloud calculated and it's put it upside down. But if we have a look at the position of the cameras, they're exactly accurate within reason to the position that they were taken in. You can see that very easily. It's created a flat surface for starters of the creek bed. And you can see here that all the photos were taken by walking along and snapshotting the ground, and that's exactly the same as the cameras that have been calculated in the scene. So if we turn off the cameras and we have a look at the sparse point cloud, we can see here that we've got the main sections of ground, and it doesn't look like there's any double projections or different errors that we can see in there. And you can basically see that although it's not very detailed and we don't have a lot of tie points connecting the photos together, it still created a fairly accurate shape and surface of what we were working with, especially with some of these little crevasses and valleys that are in the rock surface. Now, one thing we can see is we've got a little bit of extra points on the edge there, so we can easily delete those by selecting these points and just hitting the delete key. And we can also delete some of the points which we don't think are working out by going Edit, Gradual Selection, and we'll go on to reconstruction uncertainty. And we'll just drop that down and delete those as well. So gradual selection is really good for eliminating points in your models that you're just wanting to get the cleanest, best output possible. And oftentimes it really helps in the accuracy of your reconstructions and your modeling and texturing down the pipeline, to be able to delete these points rather than keep them in there. So now when you're happy with what with the sparse point cloud, you can then create the dense point cloud. So one thing that's important to note is the better and the closer the points in your sparse point cloud, the better reconstruction you're going to get in your dense point cloud. Basically what this information here, this data here is telling us is that we didn't have enough overlap in our photos when we were taking the photos of this ground surface. The more overlap that you have in the photos and the more densely you pack in those photos with the camera, the more densely packed in this sparse point cloud is going to be, because it's got more tie points and it's got more coverage of the area. You can see here that these cameras are fairly spaced out. You can see here that there's a few meters in between each one of these cameras as they've been shot on this environment, and there's gaps as well where they've been shot. Now that's usually because there's been an obstruction like a rock or a tree in the way, so you can't actually get into those locations. However, the more overlap that you have with the software, the better results that you're going to get. The other thing I was going to show you quickly is the official information I got from PhotoScan regarding photography of all PhotoScan surfaces. I'll just bring that up quickly because it's really interesting in relation to these ground surfaces. So this is a response to an email asking the software team at Agisoft PhotoScan what is the best possible way to photograph surfaces like these rocks to get the best results, what kind of lenses to use, what kinds of depth of field and things like that, and what kind of camera. So what they wrote back is generally all capturing requirements for most types of objects like trees, buildings, and rocks and rainforests and all kinds of things will be exactly the same. The quality and resolution of the reconstruction depends on multiple factors, and here are the most important of them. The resolution of the images. So for example, if we look at this image here and we get info, it's got here 5472 by 3648. So the higher resolution the images are that you're starting with, the better reconstruction results you'll get out of PhotoScan. So that's the focal length and the distance to the object, and that allows you to create high resolution results. Also using a 50mm lens, meaning like if the image is zoomed right out on the whole object on a wide angle lens, what that's going to mean is it's trying to pack a stack of texture data into a large area rather than being really zoomed in and putting that texture data and geometry data into a smaller area. So if you're using 50mm lenses, which are more zoomed into surfaces as opposed to 24mm lenses and things like that, what you're going to get is much better resolution in your geometry and in your textures from that focal length. The other thing is better overlap will result in more stable alignment and reconstruction results. So once again, we're talking about the overlap in this model and how there wasn't enough overlap on the rocks, and how if you had more overlap, you would get a denser sparse point cloud, which would create a better dense point cloud. So the other thing that they said is the camera model, so 6D, 1D, using Nikon or different cameras is not very important as long as the photo quality is good and the images are sharp with low noise. So to get low noise, that's by using an ISO of 100 and trying to get the ISO as close to 100 as possible will give you low noise in your images, especially if you're using low light, photographing in low light. Additionally, they say we recommend to pay attention to the focal depth to avoid image blur caused by the shallow focal depth. So for example, in this image here, you can see here that the left side of the image is in focus, whereas the top part of the image is out of focus. Similarly, on this image, the foreground is in focus and the background's out of focus. That is because if we have a look at the info here, the f-stop is set to f4, whereas we could have set that to f11 or f14 and given it a much better, sharper image, except we would have needed to use a tripod to do that. So these were just handheld shots when I was first going out on trips to get these photo scan data sets before I was using a tripod to shoot the scenes. So but I was using a very expensive camera and a fast image stabilizing lens, so I was able to get a lot of sharp photos without a tripod. But if you're using, if you want to eliminate the depth of field coming into the background and eliminate motion blur, you can just use ISO 100, and you can use the highest f-stop the camera goes to, and you can just shoot it on tripod on manual settings, getting raw images, and you'll get excellent reconstruction results from your images, especially if you use a lot of overlap. So once you're ready to generate the dense point cloud, and now we've discussed how to photograph the scene really in an ideal scenario, you go to Workflow, Build Dense Cloud, and we're going to set that to high. And the other option with ground surfaces is you can set them to ultra high. The ground surfaces, because of the lack of three-dimensional data, like they're not like a person or a rock or like a car, they're not covered with every angle with geometry and surface detail. The surface detail is more or less flat in one axis. It's like straight down in the Z axis. So when you set it to ultra high, you're actually going to get a huge amount of detail, and basically it's going to reconstruct the ground using every pixel from the image that you're using. So you can set the ground surfaces to ultra high and then set the rest of your scene, like trees, individual rocks, characters, vehicles and things like that, to high, and you'll get excellent reconstruction results from that. It's also faster to generate the dense point clouds of ground surfaces than it is for total 3D objects, because the depth is easier to calculate. So once you're ready, just hit OK, which with whatever setting you would like to use, and you just wait for that to process. So once you're happy with that, you should have a pretty cool dense point cloud of the surface, and you can see here we've got excellent geometry detail and texture detail that we can see even just in the dense point cloud of this surface, and that's what you're aiming for with these dense point clouds. Now don't be worried if there is what appears to be holes or gaps in the dense point cloud, because they will actually be covered up and textured once you go to the modeling and texturing stage. So if we have a look at the finished textured model of this surface, you can see here that where those holes are in the dense point cloud, like here and over here, once you actually go to the textured version, they're completely eliminated and filled in with textured model. So don't necessarily think that just because there's parts of that missing that it won't create a solid continuous surface for you that's going to work. Same with these areas here. It's basically where it's lacking information. It's missing projection data where you haven't had enough overlap, or you haven't had correctly aligned photos, or maybe you had a blurry photo in that section that you disabled, and that's why you haven't got enough overlap. So basically, it will still create geometry and texture map on those surfaces that you've got without too much hassle. So once you've got the dense point cloud created, all you have to do is go through the same exact processes that we've done with the roots and with the tree. If you want to go back and have a look at those videos, by all means do so. But all you do is you go through the workflow and you build mesh at high settings and the way to break it up into sections is you drag the bounding box around the section of the ground that you want to create a mesh for. And what that'll do, it'll allow you to force detail, texture and geometry detail into the section of rock and ground that you want to work on. So if you had this ground surface, for example, you could break it into 3 sections with 5 million polygons in each one and 16K textures, and that'll get you a much better result than simply meshing and texturing the whole entire surface with a single texture. You'll just simply get a lot more detail and a lot more resolution from the geometry and the texture information. Plus, it'll be easier for the easier to manage in smaller pieces when you're working with it. So you just basically the process is you build the mesh, you export the mesh into ZBrush and fix up and paint any objects that you need to fix up, any sharp edges, the same as what we did on the tree, and then you bring it back into photo scan by going onto tools, import mesh, and bring the geometry back in, and then you go to workflow, build texture, and you create, keeping the UVs, you create a mosaic texture at 16K, and then you'll have the texture map on the geometry. And the final step to get it ready for Maya is to go File, Export Model. Once you have your textured model, and you simply save it as rock, ground, textured, and that will basically save the texture as a TIFF and save the file in there too, and that'll be ready to use in a RenderMan pipeline after you've done that. The last thing we're going to have a look at in the next class is the entire scan of the whole rainforest, and there's lots of different tips and techniques I can give you for large-scale scanning environments where you're using massive data sets that will bring any high-end workstation crashing into the ground in burning flames and smoke. So the point of working with massive data sets, and why I've given you this scene, is because that's what you'll be working with in the film industry, is massive data sets and huge scenes. Not only that, it's actually a really interesting, really super interesting thing to see the entire world recreated as a colored point cloud and be able to have it texture mapped and have geometry put on it. I mean, it's just like such a complicated interlinking geometry and texture detail with so many different components to it, and there's so many different elements in the one scene all interlinking onto itself. It's amazing to be able to see that how that all works in the Agisoft PhotoScan software, and how it actually connects together and can illustrate these huge scenes. It also opens up possibilities for new ways at looking at visual effects and navigating environments, and asking questions like, why is there any specific reason why the future of computer graphics is there a reason why the future of computer graphics needs to be textured lit polygons? Maybe we could be looking at a very detailed environment as a point cloud where all the points make up the subpixels of the scene, and there's a lot more geometry and texture detail than you could ever hope to get with polygons and displacement maps and things like that. I mean, the detail in this scene has got, we're looking at graphics here that have no UV maps, no textures, and no polygons. It's just actually colored points that are unlit that are in the scene. And you can see here that there's just a massive, enormous amount of detail and geometry detail that you can get from these 3D colored points cloud scans. The other thing that is important to discuss is that you're able to do this on a fairly low-end computer, like a laptop. Eventually in the future, you'll be able to do this on mobile phones. So you'll be able to walk through an environment taking thousands of photos, and then you'll be able to assemble that into a 3D point cloud data set on the sort of next-gen mobile phone handset that you've got. For certain, that'll be a future option where there's a sort of Agisoft PhotoScan software that recreates 3D point clouds of the photos that you're taking, similar to the panoramas and other image editing tools that are already on phones. So I think that's a realistic, a realistic future prediction that we'll be able to build these massive 3D data sets on our phones. So yeah, it's really fun exploring this, exploring all this point cloud data, especially if you've been to the real environment and you recognize the locations that you've been to. Definitely you'll see 3D travel photos on Google Maps and Google Earth. You'll see pins dropped that'll be 3D recreations of different scenes that people have shot and filmed on DSLRs and on mobile phones. And basically it'll be just an awesome thing that is like 3D photography, I guess. That'll be a new format of digital imaging that'll give people the ability to look at environments and as 3 dimensions and have it render in real time on their computers and phones so that they can explore it and check it out. So we're going to have a look at that scene and look at the daunting task that it was to actually reconstruct it, as well as different things to do with memory on workstations, to do with the number of photos that are the limitations of workstations and the software, basically, as to what you can realistically reproduce, and ways to generate this into polygonal graphics. So we'll have a look at that in the next class.